slides, and I'm not even sure who's presenting. Because, yeah, somebody, one of the authors is presenting, SELVAM. Okay, can we play it?
Hello everyone, my name is PANNEER SANTHALINGAM. I am an assistant professor at Brooklyn College, City University of New York. I am here to present our work on synthetic smartwatch IMU data generation from in-the-wild ASL videos. This work was done while I was a PhD student at George Mason University in collaboration with HUZEFA, RANGWALA, JANA, KOSECKA, and PATHAK. Let me start by briefly introducing American Sign Language. It's a visual spatial language wherein the speakers use bodily movements, hand gestures, and facial expressions to communicate between each other. ASL is being used by more than 500,000 people in USA and Canada. Because of the nature of the language, some of the voice-based technologies like home assistant systems and driver assistant systems are not available for ASL speakers. There is also this gap between ASL speakers and non-ASL speakers. Building automatic ASL gesture recognition solutions can help us alleviate this gap. Building them using smartwatch, that is the IMUs that are present in the smartwatches, has an added advantage that these solutions have fewer privacy concerns compared to cameras. And also, the smartwatches have a higher adoption rate, and we could take advantage of that and get these directly to users as soon as possible. These automatic ASL gesture recognition solutions depend on machine learning models which have a predefined pipeline of collection, training, and prediction. These machine learning solutions, they depend on large data sets, as we have seen in some of the recent advancements in natural language processing and computer vision. There is a significant gaps in terms of these data sets for cameras and IMUs, that is the smartwatches present in the IMUs for ASL gesture recognition. The table here shows statistics for camera and IMU in terms of publicly available data for ASL gesture recognition. As you can see, there are more than 1 million samples for camera, while we have just thousands of samples for IMU. This raises an obvious question. Can we somehow take this large video data and generate IMU data? If we can do that, what that can enable, right? So if we could do that, we could take these data, take these videos, generate IMU data from them and train models. And when an ASL speaker wants to do ASL gesture recognition, he can directly use these pre-trained models to classify ASL signs without having to go through the laborious process of collecting IMU data, labeling, and training models using them. Motivated by this, we have proposed a framework which we refer to as VA to IMU, short for video to IMU, to generate and synthesize IMU data from the videos. We start by using existing post-estimation approaches to extract 2D body key points and transform them to 3D. Following this, we propose two modules, one for orientation estimation and another for acceleration and gyro estimation. The question is, if we have the 3D key points, we already have the 3D wrist position. We can track this and compute acceleration, right? The problem with this approach is that IMUs and cameras, they have a different perspective of the same moment. So when a user is moving his hand towards the left, as you can see here, IMU see that as a moment along the x-axis, while a camera which is present in the environment, it sees it as a moment along the y-axis. We need to compensate for this difference in perspective. To do this, we need the orientation of the IMU in the camera's frame. And we could also take advantage of the fact that smartwatches are worn on the wrist, and we could approximate the wrist orientation as a proxy for the IMU orientation. And we could model the orientation as a function of hand and arm joint positions that we have in 2D already. The challenge here is that there are some missing hand joints that are the result of motion blur observed in publicly available ASL videos. And this translates into incorrect orientation estimations. While this presents a challenge, I would like to make the following observation, which is that the amount of motion blur varies across different frames, as you can see here. And the hand shape is consistent across all the frames that we see here. So we could actually take the hand shape and propagate it from frames with lower motion blur to the frames with higher motion blur. To do this, we start by classifying the frames. The ones with lower motion blur, we call them key frames. The ones with higher motion blur, we call them delta frames. We take a group of these frames and we propagate the hand shape information from the key frame towards the delta frames. To do this, we have a caveat, which is we need at least one key frame amidst a group of delta frames. Additionally, the keyframe can appear either before or after the delta frame. Hence, we need a bidirectional approach. We have used bidirectional LSTM-based models to address this. These models take as input the 2D arm and hand joint positions, and they estimate wrist orientation as a function of them. Once we have the orientation, now we have addressed the challenge of the difference in perspective. Maybe now we can compute the acceleration, and we also have the orientation. We can take a derivative of that and get gyro from them. We still have two challenges. The first one is that there's a difference in sampling rate between cameras and IMUs. The videos that we are working with are captured at a lower frame rate. To address this, we interpolate the video frames to match the sampling rate of the IMUs. The next challenge is because IMUs are worn on the wrist, they capture finger movements. This has been established previously in research in addition to wrist movement. So we need to model the acceleration and gyro as a function of both the arm as well as hand joint movements. For this, we have proposed a multitask deep learning model. The model takes as input the 3D arm and 2D hand joint positions and wrist orientation and estimates gyro and acceleration. This model consists of a shared set of LSTM layers like the ones that I'm pointing to. These cells helps us to learn shared feature representations for both the tasks, which is followed by task-specific layers. Here, multitask deep learning is going to help us to better generalize by making the model focus attention on only the relevant features. To evaluate and train the models, we have collected our own synchronized data with IMUs and cameras, and we have trained and evaluated the modules, which I'm not going to go into in the interest of time. For the end-to-end evaluation, that is to show that this framework can be used directly as an out-of-the-box ASL gesture recognition solution, we have taken the MS-ASL dataset, picked 70 gestures. This is a publicly available data that anyone can make use of. We have translated and generated IMU data using our BA to IMU framework that we proposed. And now we have collected data from 9 users for the same 70 gestures. Now we are going to use this collected data to test the model which have been trained on the translated data. The table here shows the results for different number of gestures, 50, 60, and 70, for different training strategies. In the interest of time, I'm not going to go into what do I mean by augmentation here. So we have 3 strategies. One is with only the translated data with augmentation. The second one is just using the collected data. And the third one is a combination of the two. The first thing I would like to highlight is that the VI to IMU generated data with the augmentation has comparable performance with the collected data. This shows that we could have out-of-the-box solutions for ASL gesture recognition without having to collect any data at all. And the model with the combination outperforms the collected data by a significant amount because it takes into account of diverse data, it is able to generalize well, and it has a large amount of training data for training. With that, I would like to thank you for listening to my talk. If you are interested in our work, please refer to our work. Thank you.
Okay, that was the warm-up. Welcome to the session 4A on accessibility.